All right, now let's talk about um, measures of dispersion. We already looked at the measure of central tendency, which was expected value and median, two of them, by the way. Now let's look at the measures of dispersion. So for dispersion, you have seen these things from statistics. These are very simple concepts: variance and standard deviation. So for variance, we say how far on average is x from its mean. So on average, this is key. How far on average is our x random variable from its mean? And the standard deviation is simply the square root of the variance, right? So the standard deviation is easy to get it when you know what is the variance. So let's assume that the expected value of x is equal to mu, and then we can define the variance like this. The variance of random variable x, remember guys, we showed these random variables with capital letters. The variance of random variable x is how far, let's translate this English to mathematics. On average, how far is x from its mean, right? On average, how far is x from its mean? And we have to square it, because if I don't square these things, positive negatives are going to cancel out each other, and we don't get the right measure of the dispersion. Okay. We can also mathematically prove that. Again, this is beyond scope of this course. Not beyond scope, it's easier than what we learned in the course, but we don't necessarily prove it here, but this is an exercise. I'll prove. How can we go from this part to this part? It's not that complicated. You only need to open up this thing and then use the properties of expectations in slide, I think 3 or 4, we talked about it, and then try to go from this left part to the right part. All right, when we know what is the variance, we can easily come up with the standard deviation, which is the square root of variance. And graphically, what is the definition of variance? It's a measure of dispersion, right? So for instance, in the green line, the standard deviation is 1, so the variance is 1. The red dashed line, the standard deviation is 2, so the variance is 4. And that's blue dotted line, the standard deviation is 3, so the variance is 9, right? Which one is more dispersed? Of course, the blue one. So what does it mean? It means that the variance is higher. So that's simple. Okay, so again, intuition of all these things is really straightforward. Okay, now let's look at some properties. First one, standard deviation is easier to interpret than the variance because it has the same unit as the expected value. So this is I think you have seen this before. So for instance, if I have a random variable and my random variable is wage, okay, and I'm looking at the distribution of wage. Let's say it is right skewed. I have a bunch of millionaires here because of that, it makes it right skewed. And I want to calculate the variance, right? So look at the definition of variance. Variance is the expected value of x minus mu to the power of 2. So the variance, the unit for the variance is going to be whatever the unit for wage is, which is dollar squared. Does that make any sense? No, you cannot interpret dollar square. So for that reason, we take the square root of that, we call it standard deviation. And what is the unit of standard deviation? Dollar. It's the same as the unit of your random variable. So that's why we're going to stick to standard deviation when it comes to interpretation, because it makes more sense. We can relate to this number a lot easier than the variance. But both of them are telling you the same story. If variance is higher, standard deviation is higher. If variance is lower, standard deviation is lower. But in terms of interpreting the units, you should not interpret the unit for variance because it's a square. If you're talking about, I don't know, age, it's the age squared. Does it make any sense? Not at all. Okay, if you're talking about dollar square, doesn't make any sense. So that's one thing. Another thing, let's quickly review the properties of the variance. We already reviewed the property of expected expectation, expected values. Now let's look at the properties of variance and standard deviation. All right, so the variance of any constant is 0. This should be also straightforward. So if I have a random variable is taking only one number, 1, 1, 1, 1, 1, 1, what is the variance? 0, because There is no measure of dispersion here. You're centered at one. Imagine this is my random variable, and the random variable is x, is only taking one value. What is the dispersion? 0. What is the expected value? Exactly that number. So if this is 10, so expected value of x is equal to 10, but the variance of x is equal to 0. So standard deviation is also 0, right? So that's property number 1. Number 2, for any constant a and b, the variance of ax plus b is equal to a squared variance of x. Okay, so how do we get this one? So this one is easy. B, I can get rid of any constant because variance of any constant, we just talked about it. The variance of the constant is 0. So the variance of the constant is 0. Then I have to figure out how can I go from variance of ax to a squared variance of x. So for that, you have to use the formula. Okay. So again, proof exercise, but this is the sketch of the proof. So expected value of, remember the definition of variance, we can, I don't know, for instance, we can use this one. Yeah, this one. X minus mu to the power of 2. Now, if I, instead of x, I write ax, then the average is going to have a mu in itself, because the average of, if I multiply random variable by a, the average is going to be multiplied by a, so I can write ax minus a mu. I can factor out the a, x minus mu. Then when I square it, so I have a squared expected value of x minus mu squared. There you go, I have a squared variance of x. I just proved it for you. All right, again, guys, I'm not expecting you to know any of these proofs, but when it comes to the properties, you must know them. If you're curious how we prove this, this is the answer. But if you're not curious, you should know the application. The variance of ax plus b is equal to a squared variance of x. In homework 3, you need this thing. And finally, very important one. This has a huge application in finance. The variance of a sum is not equal to sum of variances. So what are we talking about here? We're saying the variance of x plus y, two random variable, is not equal to variance of, this is good news for finance, plus variance of x, variance of y. Okay, and when I say it has a huge application in finance, you know, in portfolio analysis, we know that if I have, let's say x is Apple, y is Walmart, right? And I'm going to say that if I make a portfolio of Apple and Walmart stock, the variance of that portfolio is going to be less than the variance of Apple plus variance of Walmart. So this is really, really good news. It means that you can diversify. You can diversify your portfolio and come up with a smaller variance. And what is a smaller variance? It means that your portfolio is less risky. Okay. So let me postpone this discussion to the, when we talk about the correlation and covariance as well, and we get back to this discussion. But for now, just remember, the variance of the sum is not equal to sum of the variances. For expectation, however, we talked about it. The variance of the expected value of the sum was equal to the sum of the expected values. These are really important properties. All right, so let's move on to the next slide. Now let's talk about standardizing a random variable. So we also call it Z transformation of X. And from a statistic, so you know this, you may have heard about Z-score. So this is something that we call it standardization. But why do we standardize a random variable? So imagine we have 3 different random variables. Let's call them X, Y, Z. And X is the number of heads when flipping a coin 3 times. What is the unit? 0, 1, 2, 3, right? Y is the stock price in the past 12 months. What is the unit? Dollar. 120, 220. Again, it can be anything. These are just simple examples. And let's say Z is height of US teenagers at age 11. So it can be something between 110 centimeters and 160 centimeters, right? So I have 3 different random variables. The magnitude is different. The unit is different, you know, centimeter, dollar, and then just counts, right? So unit is different, magnitude is different. How can I compare these the distribution for these random variables, right? So in order to answer that question, in order to make sure that you can compare apples to apples, you have to do a transformation. That's one of those transformations which is very commonly used is called Z transformation. Or, oh, actually, let me change this one. You don't confuse. This is just a name. Call it W. Z stands for standard normal distribution, so it has a separate meaning. So we call it the standardization or Z transformation. And how do we do that? We say whatever your random variable is, if it is X, take the average out. So we call this process demeaning. Take the average out. Demean. Take the average out and then divide it by a standard deviation. So we call this new random variable Z. So for the first one, you do something like this. For second one, you do something like y minus the average. So let's call it mu x. You know that these mu's are different. So let's call it sigma x, sigma y. We can call it z y, zx. And then finally, for the third one, we have w minus mu of w. This is the average of w divided by the standard deviation of w. This is zw. Now I can compare, I could not compare x with y with w because it didn't make any sense. However, I can compare zx, zw, and zy. So that's the beauty of Z transformation or standardization, right? So we already talked about this one. And we know for a fact that if you do that, this Z has the average of 0, mean 0, and standard deviation 1. All right, so, and it is very interpretable. You know, you can interpret Z. You can say Z measures how many standard deviation you're from your random variable. So, your random variable is from its mean. So for instance, Z of X means how many standard deviation is your X from its mean. Z of W means how many standard deviation is your W from its mean, right? So let me give you one example for yn, so for these two. If I say z of y is equal to 1.5, what does it mean? It means that the stock price is 1.5 standard deviation above its average. I don't know what is the average, okay? What is the average of the stock price? But I know that 1.5, so that observation was 1.5 standard deviation above the average, okay? Let's look at another example for W, height. So if z of W is equal to 2, means that this guy, this observation is 2 standard deviation above the average, right? So we know that this should be a very tall guy. This should be a very relatively high stock price. So if I'm looking at another individual in that teenager sample, and if it is equal to -2, this means that that boy or girl is 2 standard deviation below the average. So I know that he or she is short, he or she is tall, right? So this is very interpretable, okay? And more importantly, the probability distribution of these standard random variables are often virtually identical. Well, we're going to talk about it next class when you see the normal distribution. So this Z standard, they have normal distribution. They all of them have normal distribution. So that's why we say it's virtually identical. All right, so let's move on. Okay, we can speed up here because the rest of the materials is really straightforward. You should know from your statistics, and you have worked with them a lot. I don't expect you to memorize any formula from this slide onward. Okay, we don't care about the calculations because we're going to use R or Python or any other programming language to come up with these numbers. But I want you to understand the intuition. So the first one is measure of symmetricity, skewness. What is a skewness? Skewness tells you that if your distribution is left-tailed or right-tailed, right? So we have negatively skewed versus no skew versus positively skewed. Or sometimes we call it left skewed, the negative skew, left skewed also, left. This is center and this is right skewed. Okay? These are different terms. And if that's the case, this is what I want you to remember because this is important. Especially in econometrics, it is important. Sometimes our independent variable or dependent variable are not normally distributed. And especially if the dependent variable is not normally distributed, it brings some problem to on the table. We have to discuss those problems. We have to make assumptions and etc. So it is important for us to realize that if our random variable is skewed or not. And how do I know that when I give you a shape of distribution, how do I know that it is left or right? So you look at where the tail is. Tail is on the left, we call it left skewed or negatively skewed. Tail is on the right, we call it right skewed or positively skewed. And when when it is symmetric, there is no skew. We can calculate the skewness using this formula, but again, we barely care what is that formula because we just look at a number, if it is equal, if it is positive, negative, and etc. All right. Next slide. Please, next slide. I don't know why it doesn't go to the next slide. Let me pause the video. I don't know why it doesn't change the slide. All right, I was finally able to change the slide. Yeah. So here's an example. This is a distribution of household income in US. And I think in all around the world, that's the case. It's a very well-known fact that the household income is a very skewed distribution and it's positively skewed. What does it mean? It means that we have a bunch of millionaires here. And if you have a bunch of millionaires there, it's going to affect the average. So you should not rely on the average. And by the way, from the previous slide, I forgot to mention that. So the whole point of this slide is this. I forgot to mention that one. Sorry about it. So if it is left skewed, mean is less than median, less than mode. If it is right skewed, mean is greater than median, greater than mode. So let me write it for one of them. If it is right skewed, mean is greater than median, median is greater than mode. And for the left skewed, the other way around. All right, so let's go one slide. So we know that 50th percentile, it's the median. So this is the number that we should rely, not the average. Okay, so the average is going to be skewed. So maybe average is, if you calculate the average, we get something around, maybe for this example, we get around $90,000, somewhere around here, which we know it is biased. It doesn't make any sense. So we have to report the median as the measure for central tendency in the data. All right, so let's move on to the next slide. Now let's talk about the covariance and the features of joint distribution. So whatever we talked so far, we talked about separate random variables like X, like Y. For instance, one of them was wage. We could talk about height. We didn't say anything about their joint distribution. So that's what we're going to explore here. What is their joint distribution? Another color. And make sure that it is not that thick. All right, so we call it measure of association or joint variability, and it has something to do with what will happen to one variable if we change another one, right? What is the co-movements between variables? So we call it joint variability. So one of those variable measures are covariance. The other one is correlation, right? So what is covariance? Again, plain English, we say on average, how two random variables vary with each other, right? And mathematically, we show it this way. On average, how two random variables co-move with each other. And so what does it mean? It means that if X and Y goes up and down together, what do you expect to see for the covariance? Positive or negative? It's going to be positive, right? If they go up together and down together, so the covariance is positive. If one of them goes up, the other one goes down, what is the covariance? Negative, right? So, and the magnitude, you can mathematically calculate the magnitude. And by the way, we can prove this thing as well using the properties of expectations that we explored in the previous slides, we can prove. So this is exercise. No need to say none of these things are testable. But you need the intuition at least for the rest of the semester. So this is definition of covariance. What are the properties of covariance? Number one, if x and y are independent, then the covariance is 0, right? And when we say independent without specifying it, remember it's strong. If someone, or if you're reading a textbook that simply said independent without specifically saying strong or mean, they mean strong. So if two random variables x and y are independent, so the covariance is going to be 0. Remember, what was the definition of independence? The probability of y given x was equal to probability of y. So the probability of y had nothing to do with what is the value that you're conditioning on based on x, right? So this means that x and y are, the covariance is going to be 0. If one of them goes up, the other one doesn't do anything. If the other one goes down, well, the first one doesn't do anything, right? So that's how we define a covariance is equal to 0 if two random variables are independent. And then 2, for any constant a1, a2, b1, b2, the covariance of ax plus b1, a1x plus b1, and a2y plus b2 is equal to a1, a2, covariance of x1, y. So where is this coming from? Do you remember that the variance of a constant was 0? Imagine I'm looking at, let me simplify it with another property. What is the covariance of x and a constant? What do you think? Think about intuition. So x is going up and down, and another random variable is constant. So it's not doing anything. So it's 0. So the covariance of a random variable and a constant random variable with a is going to be equal to 0, right? So we can easily get rid of these constants. Then we say the covariance of a1x and a2y is going to be a1, a2 covariance of x and y. Do you remember that I proved to you that the variance of ax was equal to a squared variance of x? The proof is going to be exactly the same, but we're using the definition of covariance instead of variance. So again, this is another exercise for your, if you want to have fun with some proofs. If not, at least you should remember these properties because these are important. And finally, this one is one of the most important properties that, again, has huge application in finance and portfolio analysis. And you need to use this one for homework 3. What does it say? It says that the variance of ax plus by is a squared variance of y, x plus b squared variance of y plus 2ab covariance of x and y. But this means that if you come up with two stocks that have negative covariance, so if the covariance between x and y, if the covariance between x and y is less than 0, then the variance of a portfolio is going to be less than the variance of the summation. So that this is really, really helpful, right? So again, what does it mean in plain, simple English? If you want to construct a portfolio of stocks, right, make sure you pick the stocks that are negatively correlated with each other and put them in portfolio. If you do that, you're reducing your risk. Of course, you're reducing your return as well, but that's a separate argument for finance students. Just remember, if you look at variance as a source of risk, the variance of the summation is going to be less than the sum of the variances only if the covariance is negative. So this is the implication. Variance of sum is going to be less than the sum of variance if they're negatively correlated. Portfolio analysis. All right, then let's move on. Again, guys, when I say that, the homework 3, well, remember, you need these things for homework 3. I think I mentioned homework 3 multiple other times, so make sure you watch the video and take notes. Finally, correlation. Okay, so do you remember we said variance, the units was nonsense, so we went to standard deviation? Exactly the same story. So covariance, the unit is nonsense, we go to correlation. Correlation is always between -1 and 1. However, covariance can be -infinity, +infinity, and but they're telling the same story. If variance is higher, the dispersion is higher. So the same as the standard deviation. If covariance is positive, two random variables are moving up and down together. So correlation is positive, right? Mathematically, let's go over the intuition first. Correlation tells you that on average, it measures the linear relationship between two random variables. And I cannot emphasize how important is this linear. I cannot emphasize more how important this term linear here, linear relationship. I'll give you an example. And guys, remember in this course, all you're doing is looking at the linear relationship between random variables. So this is a really important observation. Whatever we do in econometrics in this course, at this level, has something to do with linear relationship between random variables, and that's correlation. Okay. And I also said that the covariance depends on units. How, for example, the covariance of education and earning, I don't know, for instance, this is some example. It depends on the unit. So for instance, here, the earning is dollars, $1,000, and education is years. So the covariance is a mix, right? So in order to get rid of that lack of interpretation, we go to correlation, and correlation is unitless. There's no unit. It's always between -1 and 1. How we define it? Correlation is defined as, this is a mathematical formula, as a covariance divided by standard deviation. It's some sort of a standardization. So whatever the covariance is, if you divide it by a standard deviation of x and a standard deviation of y, then you get to the correlation. And there are some other, there are some other letters that we use. For instance, instead of covariance, we sometimes show it with sigma xy. For standard deviation, we do it by sigma x, and standard deviation of y, sigma y. Okay, these are basically population parameters. And then rho, we usually show it for correlation. But again, don't get overwhelmed by all these formulas. Apart from homework 3, which is not testable, by the way, you're not going to see these things specifically for the rest of the semester. All you need to know is the intuition. So what is the intuition for correlation? This one, correlation is positive. This one, correlation is 0. This one, correlation is negative. And correlation is always between -1 and 1. And finally, the correlation of a1x plus b1 and a2y plus b2. We can get rid of these ones because the covariance is 0. And more interestingly, we can get rid of all these things as well. So what does it suggest? It suggests that if you have two random variables, right, x and y, if you multiply them by any number and add a constant, the correlation is not going to change, right? And this is what we capture in econometrics. So in econometrics, at the end of the day, what we capture is the correlation between random variables, but the goal is to move beyond those correlations by controlling for more explanatory variables. So this is the gist of the course. At the end of the day, we want to go from correlation to causation by controlling for more explanatory variable. And what are we measuring in econometrics? One last time, guys. The linear relationship between random variables. So let me give you an example, which is going to be very fun, actually. Let's say I have two random variables. I have random variable x, and I have a random variable y. And this y happens to be x squared. I can perfectly have two random variables like this, x and x squared. If I plot x and x squared, and then let's say y is x squared plus some noise. And don't worry if you're not following, but just wanted to, graphically, you should be able to figure it out. So let's say this is the data. This is the data. Okay, so this is the data. And it is symmetric. So let's say it goes from -5 to +5. Okay. If you calculate the correlation, for all these observations, what do you think you get? You will get 0. So if you use any kind of mathematical programming language like R, and you pass this information into it and you calculate the correlation, you would get 0. Because of what? Because there is no linear relationship between the two. Does everyone agree? There is no linear relationship between the two. However, we know that for a fact there's a perfect nonlinear relationship between the two, right? So this cannot be captured by correlation. All right, so pay attention that the correlation captures the linear relationship between random variables, and that's what we do in econometrics. All right, so finally, let's get to our last slide, which I promised you that this is something that's going to stick with us for the rest of the semester. So let's use another color. Now we are ready to read all these things on this slide. And I want you to, I don't know, understand the intuition. If you don't understand it, memorize it. This is very important. My first goal is for you to understand it intuitively. But if for whatever reason, you forgot things, you tend to forget things, just make sure you memorize. You stare at this slide for many minutes until you feel comfortable that, okay, I memorized this one. Because we're gonna see this again and again and again. What does it say? It says that independence, the way that we define independence, will lead to mean independence, and mean independence will lead to correlation is equal to 0. However, the other way around does not work. You cannot conclude if I have two random variables that the correlation is 0, I cannot conclude that they're mean independent. And I cannot conclude that they're independent. However, if I have two random variables that they are strongly independent, I can conclude that they're mean independent, and I can conclude that the correlation is 0. Okay. And this is also very important. Conditional expectation captures the nonlinear relationship between x and y. So this is going to capture this one. Conditional expectation captures a nonlinear relationship between x and y. However, correlation captures the linear relationship between x and y. Okay. Now, let me go back to our simple example with wage and gender and see how we can apply it there. Right? So take a picture of this slide, have it in your mind, and now let's go to the whiteboard. So this is our friend. So number 1, we answer this question if they are strongly independent. Number 2, we answer this question that if they're mean independence. Now number 3, you want to see if the correlation is equal to y and x is equal to 0. I know the answer, right? The answer is yes. How do I know that? Because I'm using this slide. If two random variables are mean independent, which we showed that in our example they were mean independent, the correlation is 0. Okay. So show it numerically. Maybe I leave it as an exercise, but I will talk about intuition. Okay. So let's think about intuition. Let's try to plot. Let's try to plot this, this 5 observation, and see if we can look at the correlation, if we can see the correlation is equal to 0, right? Okay, let me plot that. Here is my x, which is gender, and I know that gender can take 2 values, male, female, right? So female, male. Now look at the wage. So female, let's start with females first. I'm going to use red. Let's use red for females. What do I have? 20, 30. So let's say this is 20, this is 30. I have only 2 observations, right? So 20, 30. And for male, we were using black. So let's go back to black. So what do I have? 20, 25, 30. 20, 25, 30. Right? We already showed that they are mean independent. So let me use, guys, this is really important example. We are putting everything together in this for this class. And I understand this class was not the easiest one, but bear with me to just watch this video multiple times until you get the gist of it. So if I calculate the expected value of wage given female, what's the expected value of wage given female? Do you agree that this is 25? Does everyone see that? Between 20 and 30, the expected value is 25. And also, if I calculate the expected value of wage given male, what is it? It's going to be again 25, because 20, 25, 30, the average is 20. Now, look at the relationship between the two, right? Can you say that the correlation, what's the correlation here? There you go. Correlation is equal to 0. Do you see how beautiful is that? So from mean independence, look at the blue one. We showed that we proved it here that they're mean independence mathematically, but intuitively it's really easy and straightforward to follow. Look at the blue crosses. This is mean for female, this is mean for male. And we proved that they're mean independent. It means that regardless of the gender, the mean was equal to 25. So they're mean independence. Now, from mean independence, we can conclude that the correlation is 0. And by definition, we know correlation is going to capture the linear relationship. And as long as you have a flat line, the linear relationship is 0. Going back to this slide. There's a flat line. Oops. My God, why? There's a flat line, the correlation is 0. All right, so let's call it a day. I know there was a lot to absorb for this class, but this is all we need for econometrics from statistics and probability. I know I say all we needed. Some of you guys may say it's a lot, but this is the most, you know that the statistics and probability is huge. So we're just touching the pieces from different parts of the statistics and the ocean of the statistics and putting it together. So I'm going to show you, in this set of slides, I presented the one that you need for the rest of the semester. But of course, if you want to become a statistician, this is just the tip of the iceberg. Okay, so I'll leave you with that. Please make sure you read these slides and watch the videos multiple times, and then take the quiz, which is due on Tuesday morning. All right, with that, have a good night, everyone.